All right, so let us continue again. Oh, the second secret word is... what is the second secret word? I don't know. Juggernaut was a clear choice. I don't know what the second secret word should be. Mordock. Mordock is the second secret word. There we go. All right, so this is Morera's theorem. Let f of z be a continuous function on domain U if the integral around the boundary of any rectangle is 0. For any rectangle contained in U with sides parallel to the coordinate axis. I mean, the rectangle's got sides parallel to the coordinate axis. Then here's the punchline. F of z is holomorphic with continuous derivative f prime of z in U. This is pretty neat because this means that complex differentiable. Well, doesn't quite mean that. It means if we can prove the integral around loops is 0, then it implies that the function is complex differentiable and that it has a continuous derivative, which then, by what we were just talking about, would say that it's infinitely complex differentiable, which is kind of something. All right, so again, we're going to assume that the integral of the function is 0 around every closed rectangle. All right, and then we'll see what we can do with that. So the vanishing of a rectangular path allows us to trade the integral around, like this path. I could trade this path. I could trade that path for this path because the integral around the rectangle is 0, right? Notice that the orientation to go around the counterclockwise rectangle, let's see, counterclockwise rectangle, so I'd have what? Counterclockwise, right? So the red path is not the right way. So the reversal of the red path would actually be like this, right? Like that. And so the blue path plus the green path integrates to 0, but the red path is the reversal of the green path, so that means that the blue and the red path, when we have equality of those integrals. All right, so what we're going to do is we're going to define f of z equal to the integral over gamma, the down path of z. Now, all right, let me go on here. Where gamma down of z, let me draw a picture here. So we're starting at, oh, here's the picture. I'll do it down here. So gamma down, it starts at x naught y naught, which is here, all right? And it goes to the same y, but at x, all right? So that would be, let's see here, basically like this, at that point. That's just this part. And then I'm going to mess up the color coding if I'm not careful. Oh well. And then this y naught x to that. So it's going to go up to here. Now I've got minus gamma of d in that picture. Now this z is the point x plus iy. All right. And then, so to show f prime of z exists, we need to consider a difference. Here, the delta z is small enough to keep the z plus delta z, which is up here, right, inside the domain. And then, all right, so then we're going to calculate the difference between f of z plus delta z and f of z. So f of z plus delta z means we travel on the down, the lower, the path that goes like this. And let's see here if I can foolishly use, the blue path. I use the blue path. I unfortunately have no color printer. My wife needs a color printer at home, I think, yes. Because I need a color printer at home. All right, so, I'm just kidding. She needs it more than I do. The blue path, like this, goes from, again, z naught to, z naught's a fixed point for this construction. We're fixing it at the start, right? So z naught's just some point in D, and we're basing everything from there for the moment. All right. So I could here. Let me just take a pause here for a second. So the larger picture is that there's some set D, right? And we're taking the point Z naught, and or we're picking some point Z naught anyway, and then to get to a rectangle, we're getting to the rectangle from Z naught like that. Let me shut up. All right. So we have the down path to Z plus delta Z. We've got the red path, and we're subtracting that because we want to look at the difference of these. But when we subtract that, that would be the same as adding the reversal of the curve, which I have pictured with the arrows like that, right? Now, so I said that that's equal to the integral along the upper part, gamma u, going from Z to Z plus delta Z. So what I'm gonna do is I'm gonna replace the integral around not the half rectangle in my picture, but kind of, I'll do the path in brown for a second here, just make my picture really cluttered. So I'm saying you can replace this path around the rectangle, right? Which is what we have here, this line. So you replace that with, and I think I did it in green, with this path right here, because we are assuming that the integral around a rectangle, any closed rectangle, right, is 0. So that means that the dotted brown path and the green path must be equal, so I can replace this with that. All right. But on the other hand, it's nice to notice that f of z, is just a constant. We're integrating over w, so the integral of f of z dw over the upper path would just be, pull the f of z out, I get integral dw from that to that, which just gives me usual stuff, just delta z. Because, to get from here to here, I get delta z. Well, anyway, excuse me. The sum totals to go from here to here, we integrate dw, we go delta z. All right, so we get f of z, delta z, as I said, from this integral. Now, so what we do is we go back to star, which may be out of frame now, but this star up here, and I just add 0, which is, I add and subtract f of z, right? I add f of z, I subtract f of z, but the f of w minus f of z, I'll pull off on its lonesome, and the integral of f of z dw I just worked out was f of z dz right here, right? So then we're gonna work on this piece. You might notice that the length of the gamma u piece is 2 times the absolute value of the change in z. So if I put m equal to the supremum of these, which I can do because we assumed that f was, let's see, we assumed, how can I assume the supremum exists? Let's see here. Oh, it's continuous. So we assumed f was continuous, which means that this is a compact domain, so the supremum exists. All right, then the ML estimate tells me that the integral of this piece, right, is bounded by ML, which is actually 2m magnitude of delta z. And so let's put it all together. We got a delta z here, we got delta z there, well, the magnitude delta z there. And so if we take this expression, we divide by delta z, we've got the difference of the big F's by divided by delta z minus little f of z is less than or equal to 2m. All right, but if you look at how m was defined, m is the supremum of the difference between f of w and w. What happens is delta z shrinks to 0. Well, this gamma u shrinks to a point, which means these shrink to, m shrinks to 0, clearly, if you look at its construction. And so, as delta z goes to 0, we see that we've got this difference quotient being given by that, which is to say that f prime of z is equal to f of z in the inequality above. Furthermore, since f is continuous, we have f prime of z is continuous, and so that means that the big F is both holomorphic and possesses continuous derivative f prime of z. So we can apply corollary 9.45 to Cauchy's generalized integral formula, see that f prime prime of z, which is equal to f prime of z, exists and is continuous. Oh, this is really quite an argument. And there's Morera's theorem. All right. That brings us to Coarse Aws Theorem, which is, I think is important to include in this course because it gives you exposure to a kind of argument you may have never seen before. And you know, I think it's a quite ingenious argument. So here it is. So Coarse Aws Theorem. It's hard to appreciate in Gamelin's book because he assumes continuity of the derivative in his definition. But here's how to say it better. Let's just focus on this sentence here. The Coarse Aws Theorem says the following. If a function is holomorphic on a domain, then the mapping z maps to f prime of z is continuous. All right. So in other words, if you have holomorphic on a domain, you've got continuity of the complex derivative. All right. Here's the proof. And the proof is essentially by establishing that this condition that we have holomorphic just means that the complex derivative exists at each point in the domain. And so the argument's essentially going to be this. Assume that the function's holomorphic on a domain. Show that the integral around any closed rectangle in the domain must be 0. And then we can apply Morera's theorem to say that, well, then the complex derivative exists and is continuous. All right? That's it. So here's the proof. So let R be a closed rectangle. Sides parallel to the coordinate axis divide into 4 subrectangles. And let R1 be the subrectangle for which the integral around the boundary of R1 of f of z dz is largest amongst the 4 rectangles. So we take this rectangle, divide it into 4 subrectangles, and say R1 is the one in which the integral around the edge of f of z dz is the largest. Now, let's see here. Let's see here. So the function is holomorphic, which means that the function itself is continuous, so these integrals definitely exist. What we're after here is not continuity of the function, but continuity of the derivative, all right? So anyway, the starting point makes sense. We can calculate the integral around each subrectangle, and of course then you can pick one that's the largest. And then what you do is, rinse and repeat. Then focus on R1, divide it into 4 subrectangles, and pick the R2, which the integral around R2 is the largest of those 4 rectangles. And then you take R2 and you divide it into 4 subrectangles, and you just keep, doing this over and over again, picking the subrectangle, which is giving you the largest integral around the edge. So, of course, we have that the integral around R1 is greater than or equal to 1/4 the integral around the boundary of R. Let's see here. Or we could say that the integral around the boundary of R is less than or equal to 4 times the integral around that one. And then we get the same thing for, the relation between R1 and R2. Put this together, you got this nested, sequence of rectangles. And it's relatively simple to see that the integral around the nth one is less than or equal to 4 times the integral around the n plus 1th one. And so putting that all together, we get the integral around the rectangle that we're interested in is less than or equal to 4 to the n times the integral around the nth subrectangle. All right. All right. Anyway, as n goes to infinity, I think you can see that these nested rectangles must converge to some point, z naught in R. And furthermore, if L is the length of the perimeter of R, then L over 2 to the n is the length of the boundary of R to the n. All right. So as f of z is complex differentiable at z naught, we know that for each z in Rn, we can find an epsilon sub n such that the difference quotient minus the derivative is as small as we like, right? And so multiplying that out gives us that, multiplying by z minus z naught, we get f of z minus f of z naught minus f prime of z times z minus z naught is less than or equal to epsilon sub n times the absolute value of z minus z naught, which, by the way, is certainly less than or equal to 2 epsilon n over L2 to the n. And I've just said that the distance between a point and the center of the rectangle is no more than the perimeter of the rectangle. That's definitely true. We could be less greedy. Anyway, if we look at this function g of z, which is f of z naught plus f prime of z times z minus z naught, then that can just be straight anti-differentiated to this. All right, and so then by direct, so we don't need to assume continuity of that. Like, continuity of this is manifest. What I'm trying to say is that the continuous differentiability of this function is manifest from the given data, and because the f prime is evaluated as z naught, I'm not needing continuity of f near z naught. I just have the existence of f at z naught. That's all I need. The variability of the function is present in the z and the z squared over 2. So you can calculate this explicitly and see that the component functions are continuously differentiable. Hence, we can do the proof of Cauchy's integral theorem that we did last time to prove that this integral is 0. So I'm not assuming what I'm trying to prove by doing this is what I'm trying to tell you, what I'm trying to get at. So this integral of g of z around the boundary, our nth rectangle 0. So finally, integral around the nth rectangle, it would be the integral of this. Let's see here. So what did I do? Oh, well, remember, this is the integral of, I just added 0 because the integral of this is 0, right? But that's important because we also know that this is less than or equal to the, by the ML theorem, we have this thing right here is less than or equal to that. That's a bound for the integrand. And what's the length of the boundary of r to the n? Well, it's L over 2 to the n. So there you go. You got 2 L squared epsilon sub n over 4 to the n, where L is the length of the perimeter of R. So L is, something finite, harmless. Epsilon n is as small as you want to make it, and what happens is n goes to infinity here. Right. So, returning to star, which was this thing, star right here, we have that the integral over the nth, oh goodness, my eyes are showing. Oh, this one, this star. I'm sorry, I was looking at the whole thing. I should just be looking at this piece. So the integral over the rectangle is, because I figured out the bound on this is given by that. So I've got this, so I got a 4 to the n here, and I got a 4 to the n there, but they cancel, right? And we are left with the integral around the rectangle is equal to 4 to the n times that, which is 4 to the n. The 4 to the n's cancel. 2L squared epsilon n. L squared is finite but harmless, and epsilon n can be made as small as you like. And as n goes to 0, oh, snatching. How's the saying go? I don't know. Anyway, infinity. As n goes to infinity, we have epsilon sub n goes to 0. And so it follows that the integral around the rectangle 0. But this was an arbitrary rectangle. So we have met the criteria of Morera's theorem, and so we find f of z is holomorphic with continuous derivative on d. And that, my friends, is why it is not damaging to assume that the complex derivative is continuous. It's actually for free. Although I don't think you could really say that what we've been doing for the last half hour was free. But it's true. So there you have it. So next class I will try to focus our attention on what's more computationally important for the moment being at least, which is Cauchy's generalized integral formula. I will admit that later gets replaced with something that's even more calculationally lucid, namely the residue calculus, but we have to learn to walk before we can run, so one thing at a time. Anyway, thank you for watching these, and see you tomorrow. Bye. Or maybe I have already seen you tomorrow, which was actually yesterday. Or perhaps, I don't know. Well, anyway, I'll shut up.